Welcome to this lecture number 20 on the NPTEL course on fluid mechanics for chemical engineering undergraduate students. The topic of our discussion was integral balances of mass, momentum and energy in the last few lectures, and we are going to complete this topic by discussing one final example. Okay, and we just briefly started doing this example in the previous lecture. Essentially, it is to estimate the diameter of a free jet that emerges out of a tube or a nozzle. So, essentially you have a liquid that is flowing under laminar conditions in a tube, let the diameter of the tube be d, okay, and once the liquid exits, the diameter of the jet that emerges out of the tube is not necessarily the same as the diameter of the tube. That is because when the fluid is flowing within the tube, there are viscous shear stresses exerted on the surface of the tube that are exerted on the fluid, so which drags the fluid, whereas once the fluid emerges into the atmosphere, so this is atmospheric pressure, okay, there are no shear stresses that are acting, so the fluid tends to accelerate a little bit to reach the new steady state, okay, but when it tries to do that, okay, since there are lesser forces, let us first write down the mass balance. So, it says for an incompressible fluids d times v average is d jet, okay. Let us try to draw the balance between station 1, which is here, and station 2, which is here, okay. D times v1 is dj times vj, okay. So, v1 will be smaller than vj, okay, because of, so vj will be larger than v1 because of the fact that lesser forces are acting upon it that tends to decelerate the flow, which happened inside the tube, okay, whereas it is not, doesn't happen. So, at steady state the mass conservation states that dv1 times is d times v1 is equal to dj times vj. Since v1 is less than vj, that implies that dj has to be smaller than d, that is the jet diameter will become smaller than d, okay. That is from physical considerations. So, how do you estimate or come up with an expression for the jet diameter? For that, we can either use the integral energy balance or the integral momentum balance. So, I am going to demonstrate both. First, let us use the integral energy balance, which we did in the end of the last lecture. When you use the integral energy balance, okay, we will find that alpha 2 v2 squared by 2, the kinetic energy head is alpha 1 v1 squared by 2. I am writing the energy balance between 0.1 and 0.2 as shown here in this diagram, okay, plus or minus viscous losses, okay. Now, because we have also assumed that when the jet exits, P1 is P atmosphere, and that is also equal to P2, because in a free jet it is of course the pressure is atmospheric as we have been mentioning, but at station 1 when the jet is just about to exit into the atmosphere, we are assuming that, so this is an assumption, whereas this is almost an exact relation, okay. So, since P1 is P2, there is no P1 pressure term, and also the elevation Z1 is approximately Z2, so there is no gravity term in the energy balance. Now, about losses, we can safely neglect them, okay, because the losses in a free jet are negligible because the surrounding air is not going to exert any viscous stresses. So, the viscous losses are comparatively smaller, okay. So, we can afford to neglect them. Now, at station 1 the velocity profile is laminar, we have assumed is laminar. So, alpha 1 is approximately 2, at 2 the velocity is uniform, okay. At station 2 the velocity is uniform because it is a free jet, okay. So, uniform velocity, which implies alpha 1 is 1, sorry, alpha 2 is 1, alpha 2 is 1. So, after doing this, we will find that v1 squared is equal to, okay, v2 squared by 2, or v2 squared is 2 v1 squared. We also have the fact that pi d1 squared or pi d squared by 4 times, this is the mass conservation V1 is pi dj squared by 4 times V2. Okay. So, instead of V2 I am going to substitute. So, let us cancel the pi by 4 terms on both sides. Okay. So, you get d squared V1 is equal to dj squared times 2 V1 squared, because V2 squared is 2 V1 squared from here. I am going to substitute. So, dj squared, okay, I am sorry, let us first, before I do that, let us first square the equation. So, we will get d to the 4 V1 squared is dj to the 4 V2 squared. So, this implies that, and then now I am going to substitute V2 squared here. I am going to substitute the fact that V2 squared is 2 V1 squared out here to give, okay, d to the 4 V1 squared is dj to the 4 2 V1 squared. So, V1 squared will cancel out on both sides to give dj to the 4 is 1 by 2 d to the 4, or dj is 1 by 2 to the power 1 by 4th d, which gives dj is equal to 0.84 d. This is the result from energy balance. The jet diameter is 0.84 times the tube diameter from which the jet is emerging. Now, we can also use the integral momentum balance to solve the same problem. When you use the integral momentum balance, we will have beta 1 m dot times the average velocity, where beta 1 is the momentum correction factor, minus beta 2 m dot times the average velocity at V2, plus P1 pi d1 squared by 4 minus P2 pi dj squared by 4 minus sum of all forces acting on the jet between points 1 and 2 is 0. Now, at the jet exit, we know that the velocity profile is laminar. So, beta 1 has to be according to whatever the momentum correction factor for laminar flow is, which is 4 by 3. Okay. Now, we are going to neglect the shear stresses acting on the surface of the free jet, because it is a free jet. Okay. But this term, okay, P1 is P2 is equal to P atmosphere. So, this is P atmosphere. Okay. Now, before I neglect the shear forces, there are two contributions to the force that are emerging from a jet, on a jet that emerges from a tube. Okay. In the direction of flow. One is the tangential shear stress, the other is the fact that the atmospheric pressure, the pressure acts normally to the jet surface. Okay. But there will be a component that is acting in the direction of the flow, because the interface is curved as the jet emerges. So, there will be a contribution, the atmospheric pressure will act like this, there will be a contribution in this direction and there will be a contribution in the horizontal direction. So, we will have to take that into account. So, that horizontal force due to the normal component of the pressure is simply, so let us write this as, okay, this is the same as before, but this component, the horizontal component of the pressure that acts is simply P atmosphere times the projected area difference, which is d squared minus dj squared. Okay. So, this is the change, this is the pressure, net pressure force that acts in the horizontal direction, in the direction of the flow. Okay. So, having done that, we can now simplify the above equation again, okay, to give dj is equal to 3 by 4 to the half d. This gives you 0.866 d. This implies dj is 0.866 d. Unlike the energy balance, we got 0.84 d. Okay. So, it appears that the results that we obtained from differential momentum balance and differential energy balance are different. That is because of the fact that the nature of assumptions that we made in these two cases are different. In the differential energy balance, we said that the viscous losses in the jet are negligible, whereas here we said that the tangential component of the viscous shear stresses are negligible. So, they are not quite one and the same. So, that is the reason why we get different results when we use these two approximations. So, it so happens that this result is more close to experimental value compared to the energy balance result, because it turns out that this approximation is a better approximation, that is neglecting the tangential component of the viscous stresses that is exerted on the surface of the jet. It turns out to be a better approximation compared to neglecting the viscous losses in the jet as it exits into the atmosphere. Okay. So, this really completes our discussion on integral balances of mass, momentum and energy. Now, I am going to go to differential balances of the same three quantities, but before I do that, let me also say a few words, repeat a few things that I said on and off about integral balances. That is, they are simple, fairly simple to use because of the fact that they can be written across entire equipments. For example, you can write a differential integral balance about a pump or a compressor or involving pipelines and so on. But the price that we pay is that we need to have information about the losses, viscous losses, which have to be either obtained from experiments or they have to be obtained from a more fundamental theory. And we will see a little later that differential balances can be used to estimate losses in simple geometries like pipes. So, integral balances always come with this caveat that we cannot use them easily, that is we need to have some information about losses. Many times we may ignore losses, just as we did in the case of the jet diameter that emerges from a pipe, the diameter of a free jet, and we found that it gives an approximate answer that is quite close to the exact answer, but it can never give the exact answer. So, one has to always use the integral balances with caution as when one neglects losses or when one neglects tangential component to the forces. Okay. But little later, once we complete differential balances, we will see how we can obtain information for losses, for example, in flow through pipes and so on, and that will help us a great deal in completing the integral balances of energy, and that can which can be then applied to various really practical applications such as pipeline networks and including estimating pumping costs or power requirements for running a pump in order to make a fluid flow for a particular flow rate and so on. So, it is possible to use integral balances with some inputs regarding losses, and then it becomes very accurate. How this information comes from, whether it comes from a theory such as differential balance or experiments, that depends on flow regimes and so on, that we will see a little later. So, right now we will stop integral balances, and then we will briefly return back to integral balances when we do losses, and we will of course use them to find various things such as pump power requirements and so on, but we will now go on to differential balances. Of mass, momentum and energy. Okay. So, in integral balances we wrote we chose the control volume to be a very huge macroscopic region which encompasses equipments or even tubes and various things like that, and then we can actually carry out apply fundamental principles such as conservation of mass or Newton's second law of motion or first law of thermodynamics. That is what gave us the equations for integral balances. Now, we are going to apply the same principles to not to macroscopic regions in space, but to differential volume elements, that is very tiny volume elements which are so infinitesimal that when we do appropriate simplifications using principles of infinitesimal calculus, we are going to get equations that are valid at each and every point in the flow. Okay. So, in principle therefore, one can describe, after having solved the differential balances of mass, momentum and energy, in principle one can obtain point wise variations of quantities such as velocity, pressure, within a flow domain such as a pipe or a channel. So, differential balances give much more detailed information about fluid flow behavior, okay, compared to integral balances, but that also comes with a heavy price, because the equations that emerge out of the differential balances are much more complicated compared to the equations that we derived for an integral balance. Therefore, the solution of these equations are not easy, and often we will see that one has to go to a computer to solve the differential balances. So, it is not, solutions are not easy to come by when you write down differential balances. Okay. But nonetheless, we can, the point is one can derive equations that are in principle correct. Okay. So, provided we have the ability to solve this, then one can have the most accurate information about the flow behavior. So, that is the advantage of differential balances, while you are losing the simplicity of the differential balances. Okay, sorry, while we are losing the simplicity of the integral balances, the thing that we gain is the accuracy. Okay. So, despite having to solve a more complicated set of differential equations, that is the reason why they are called differential balances, we do have now the ability to get the most accurate flow behavior for various fluids. Okay. So, this is the motivation for doing differential balances. Having said that, at times it is not possible for us to get information such as losses by accurate solution of differential balances. So, one has to, in many cases, especially in engineering applications, in practical applications, one has to resort, or one has to take recourse to doing experiments. So, these are in some sense three fundamental ways of solving problems in engineering fluid mechanics. One is to do integral balances, the other is to do differential balances, and the third approach, especially in engineering context, is to use experimentation. And in the context of using experimentation, we will see that the notion of dimensional analysis helps us in organizing experimental data and also in getting better insight of experimental data. So, the sequence of our lectures will, the sequence that our lectures will follow is that integral balances, which we just completed, then we will spend some time discussing differential balances of mass, momentum and energy, and finally, we will proceed to experimentation as guided by dimensional analysis. So, these are the, this is the sequence of the lectures that we are going to follow in the following lectures. Okay. Okay. So, now when we come to differential balances, the first topic that we are going to discuss is the conservation of mass. We have already derived a differential version of conservation of integral version of conservation of mass. Now, we are going to derive the differential version of conservation of mass. In order to do that, we take a very infinitesimal volume, which is in the shape of a cube. Okay. So, this, let me take a Cartesian coordinate axis, okay, of width of dimensions, say delta x, delta y and delta z. The other way around, delta x is here and delta z. Okay. So, it is an infinitesimal cube. Our CV is an infinitesimal cube, because the sides of the cube, namely delta x, delta y, delta z, are very small. Okay. So, we are going to write the conservation of, we are going to write the law of conservation of mass as applied to this control volume. So, we already have our conservation of mass relation d rho dt dV. This is the rate of change of mass of present in the CV is equal to. Now, another thing we are going to assume is that since the sides of the cubes are so small, where they are infinitesimal, we are going to assume uniform velocities, because we are the region of interest through which the fluid is going to flow is so small that we can assume uniform velocity. So, I am going to write summation over all outlets, which is with an index I, rho I, A I, V I at all outlets, minus summation over all inlets, rho I, V I, A I at all inlets is 0. This is the same conservation equation. Okay. that we wrote for an integral balance, but only key difference is that now we are applying it to a very small control volume, an infinitesimal control volume. Now, when it so happens that the control volume is infinitesimal, we can make some changes to the integrals. Okay. Now, when the region of interest is so small, suppose, let me give you a very simple example. So, suppose I have a function, okay, and f of x, and I am integrating between x1 and x2. Okay. Now, that is really the area under this curve. Now, if I have the same function, but I am integrating between a very tiny difference, that is x1 plus delta x is x2, let us say, then in order to do the integration, in order to find the area under the curve, I can approximate integral f of x between x1 and x1 plus delta x as f of x1 times integral x1 to x1 plus delta x dx. The reason is because the integrand f of x is not changing much over this tiny interval. So, I can pull the integrand out of the integral. This is simply the value of f of x at x1 times the integral, which is simply delta x. Okay. So, the same thing can be said not just for a simple one dimensional integral, but also for a volume integral of the form written here. Okay. So, when delta v is very small, when the volume of the control volume is very small, I can pull d rho dt outside and write it as approximately equal to delta v. This is of course times delta x, delta y, delta z. So, that is a simplification that happens when we try to use differential volumes, okay, differential control volumes. Now, we have to look at the flux terms. So, essentially let us go back, let us write that equation again. So, integral, so that integral has become a simple d rho dt times delta x, delta y, delta z, okay, plus we have to evaluate all the flux terms rho I, v I, a I at the outlets minus rho I, v I, a I over all the inlets. Inlets is 0. Okay. Okay. So, now we have to evaluate, let us go back to the CV. The CV is a cube with 6 faces, okay. That is the control volume that we are talking about. Now, the fluid can come in via all the 6 faces. So, we can imagine, for example, so since this is the x direction and this is the y direction, imagine that the fluid can come, let us say, through one inlet and one outlet along the y direction, and one inlet and one outlet along the z direction, and so on. So, the fluid can come through any of the 6 faces and go out of any of the 6 faces. Okay. So, one thing that we have to understand is that we cannot take rho, then the components of velocity Vx, that is u v w, as constants, because in principle they can vary along the flow direction. Okay. So, in the direction in which they are flowing. So, in principle v is a function of x, y and z. The velocity vector is a function of the spatial coordinates. We have to allow for velocity variations in general. There is no need that velocity has to be constant at various points in the flow. Okay. This is as per continuum hypothesis. Okay. So, when we do that, so let us try to write the flux terms at phase x. Okay. Phase x is where the fluid is coming in like this. Okay. The inlet mass flow. So, let us try to draw, let me draw the figure again for simplicity. So, okay, this is x, this is x plus delta x. Okay. Let us assume that fluid is coming in at x and going out at x plus delta x. Okay. That is the picture we have. Okay. Of course, the fluid may come this way and go that way, that does not matter, because our quantities are algebraic, that is they have signs associated with them. So, it will take an appropriate sign, negative or positive depending on the direction, actual direction of flow. But right now just for the sake of clarity we assume that the fluid is coming through x and going out at x plus delta x. So, the inlet flow of mass at x is simply the density, which is mass per unit volume, times the volumetric flow rate of fluid entering at x, which is the x velocity, because fluid is coming in at the phase x with an x velocity, times the cross sectional area through which it is flowing, which is delta y delta z, but all of which is evaluated at x. Okay. So, outlet flow of mass at x plus delta x is rho u delta y delta z at x plus delta x. Now, a key thing comes that we have to evaluate a quantity at x plus delta x. So, we have to use what is called a Taylor series. The Taylor series says that if you want to evaluate a function at x plus delta x, where delta x is infinitesimal, that is approximately equal to the function at x plus its derivative evaluated at x times delta x plus higher order terms. So, it is an approximation, it is called the Taylor series approximation, wherein you can construct the nature of the value of the function at a neighboring point using the known value of the function, its derivatives at a original point, okay, x. So, we are going to apply Taylor series expansion at phase x. So, this term becomes outlet flow at x plus delta x is approximately rho u delta y delta z at x plus half partial by partial x of rho u, because delta x delta y are constant at x plus delta x, sorry, at x times delta x. So, let me make some space here. Okay. So, plus partial by partial x of rho u at x times delta y delta z times delta x, because the Taylor expansion is only with respect to x. So, we will pick up a delta x here. So, the net, so let us similarly write mass in at y is rho u, so rho v delta x delta z at y, mass out at y plus delta y is rho v delta x delta z at y plus d dy of rho v evaluated at y delta x delta y, so delta y delta x delta z likewise mass in at the other phase at z is rho w delta x delta y at z, and mass out at z plus delta z is rho w delta x delta y at z plus d dz of rho w evaluated at z times delta w times delta x delta y. If I substitute all these expansions in the first equation, this equation, okay, I am going to do that, then what I will get is the following: d rho dt times delta x delta y delta z plus, now let us take terms one by one. If you look at these two terms, if I have to take mass in minus mass out, okay, so these two terms will cancel out each other, or rather if you look at the first, equation, okay, you have out minus in. So, if you have out minus in, then you will find that this term will cancel this term, because they are one and the same. So, the only term that is going to survive is this will be present. So, likewise for the other two directions also. So, this term will cancel, out minus in, this will survive. Okay. So, if we write all these terms together, you will find that this is nothing but, so likewise even in the other case. So, here this term will cancel, this will go away, because that will cancel this term and this term will survive. So, when we do all this together, we will get d dx of rho u times delta x delta y delta z plus d dy of rho v delta x delta y delta z plus d dz of rho w delta x delta y delta z is 0. Now, we find that this is common, delta x delta y delta z. So, divide the entire expression by the volume of the infinitesimal element, control volume that we have chosen, that implies partial by partial t of rho u plus partial by partial x of rho u plus partial by partial y, okay, of, sorry, not rho u, partial rho by partial t, okay, rho v is 0. Now, this is essentially the differential form of the mass balance. So, this is the differential mass balance for any fluid. It is valid at each and every point in the flow. So, that is why you have differentials. Now, we can, so this equation is valid at each and every point in the fluid. So, this is also called the continuity equation. Okay. Now, we can do some simplification of this, or make this equation written in a more compact form. In order to do that, we have to recall what is the notion of the gradient operator. The gradient operator grad is nothing but I times d dx plus j times d dy plus k times d dz. This is the gradient operator. Okay. This gradient operator can act on any vector or a scalar, or you can also take divergence. Okay. So, let me explain a little bit more carefully. Okay. So, if you have this as gradient, then del dot any vector a can be written as I d dx plus j d dy plus k d dz dotted with a is ax I plus ay j plus az k. So, when I do the dotting, I will get I d dx dot ax I. Okay. This is nothing but, now I is independent of x, the direction I is independent of x. So, I can pull I out. So, I dot I d dx of ax plus, now if I take this term I d dx dot ay j. Okay. Now, I and j are orthogonal. So, I dot j is 0, I dot j is 0. So, we will not get any contribution. Okay. So, the only contribution that will survive in the del dot a operation, therefore, is d dx of ax plus d dy of ay plus d dz of az, because all the cross terms involving day dx, day dz, day I mean dAx, dy, day, dz and so on, they are all 0. So, the only thing that will survive is this. Okay. So, del dot any vector A is dAx dx, day, dy plus daz, dz, the addition of the 3 dx dx plus dy dy plus daz dz. Now, if you look at this expression here, it appears like the divergence, this is called the divergence of a vector any vector. Now, here it appears like you have 3 components rho u, rho v and rho w, and then you have ddx of rho u plus ddy of rho v plus ddz of rho w. Therefore, we can write this as d rho dt plus del dot rho v is 0, where del dot rho v is nothing but ddx of rho u plus ddy of rho v plus ddz of rho w. Okay. So, this is a compact form of the continuity equation, d rho dt plus del dot rho v is 0. Okay. This is called the vector form of continuity equation. Now, what is the advantage of the vector form written like this and the component form written before? The component form for Cartesian coordinates is d rho dt plus ddx of rho u plus ddy of rho v plus ddz of rho w is 0. This form is valid only for a Cartesian coordinate system. If you want to write it for a cylindrical coordinate system, okay, the form will be slightly different. For cylindrical coordinate systems, we will have d rho dt plus 1 over r d dr of rho r v r plus 1 over r d d theta of rho v theta plus d dz of rho v z, where v r, v theta and v z are the components of the velocity along the 3 cylindrical coordinate directions r, theta and z. Now, the form of the continuity equation is very different in the cylindrical coordinates compared to the Cartesian coordinates, while the vector form of the equation remains the same. It is coordinate free. This is the coordinate free notation. Whereas the component form is a function of which coordinate you write down the continuity equation. Okay. So, the coordinate free notation is much more compact, it is a vector form, but when you actually solve a problem, you have to refer your equations or refer your problem to a given coordinate system, and you will be it will be necessary for you to write down the component form, but you must be aware that when you write down the component form, it is the form of the equation will be very different when you choose different coordinate systems. So, the form of the continuity equation looks different when you write it in different coordinate systems, as I just showed, although I have not derived this expression, we will do that little later, but right now I am just telling you that you cannot blindly write the component form of the continuity equation in various coordinate systems in a very similar way to Cartesian coordinates, because while this form is independent of coordinate systems, okay, the component form is actually dependent on coordinate systems. So, the brief reason for that is that when you write the velocity in cylindrical coordinate systems, you will write this as Vr Er plus V theta plus V phi, sorry, Vz Ez, cylindrical coordinate system. Now, the unit vectors themselves are now functions of coordinate directions, that is, so when you go along the theta direction, the unit vector Er will change its direction. So, those will also contribute in your continuity equation. So, that is the simple reason why the continuity equation looks different in cylindrical coordinate system when you compare it with Cartesian coordinate system. Cartesian coordinate system is particularly simple because the direction of unit vectors do not change as you go along a given coordinate direction. Okay. So, that is the reason why that happens. Now, let us also simplify the continuity equation even further. Okay. So, let us consider some special cases. For an incompressible flow, an incompressible flow is defined as a flow in which the density remains a constant, it is independent of pressure. That is, whenever there is a fluid flow happening, there will be pressure differences in a fluid, but the pressure differences are not large enough to change the density, because in general we know that pressure and from thermodynamics we know that density, pressure and temperature are related by an equation of state. But for incompressible flows, we can assume that the changes in density are negligible for any change in pressure that can happen in a given fluid flow. We will of course derive a criterion as to when the flow can be considered incompressible shortly, but right now, okay, we will just write down for the simplified continuity equation for an incompressible flow. Rho is a constant, means it is independent of x, y, z and time. Okay. So, d rho dt plus del dot rho v is 0. If rho is a constant, as I have been telling, d rho dt is 0. Since rho is a constant, you can pull rho out of the gradient divergence operator. So, you will get rho del dot v is 0. Since rho is not 0, you will get del dot the velocity vector to be 0. Okay. This is the simplified continuity equation for an incompressible fluid. Notice that this is not just applicable for steady flows, this is also applicable for unsteady incompressible flows. So, we are not setting del rho del t because the flow is steady, we are merely saying that del rho del t is 0 because the density is constant, density does not change at all. Okay. This is also applicable for unsteady incompressible flows. One should not have the notion that we are throwing away d rho dt term because it is a steady flow, we are just throwing it away because density is constant regardless. Okay. So, it is also applicable for unsteady incompressible flows. Okay. So, the question is that can naturally comes to mind therefore is, when can you consider, when can you assume a flow to be incompressible? Because we just said that in general there will be pressure variations in the flow. So, when can those pressure variations be small enough that density does not change? So, in some sense what we are saying is that when we have a term like this in our continuity equation, this term is in principle rho du dx plus u d rho dx. What we are saying is that this, the magnitude of u d rho dx is very small compared to the magnitude of rho du dx. That is what we are saying. We are essentially saying that rho is constant, so this is small compared to this term, okay, compared to this term. Okay. So, if such is the case, we can argue when can this happen, okay, when can this happen. Okay. For a given dx, we can write this as u times del rho small compared to rho times del u, or del rho by rho is very small compared to del u by u. Okay. Okay. So, now we can estimate del rho by rho using thermodynamics. In thermodynamics, it turns out that delta P, the pressure difference, is approximately the speed of sound squared times the density difference. So, if there is a pressure difference, the corresponding density difference will be given by speed of sound squared. Okay. So, for example, if you have a pressure difference, the density difference is given by del P by Cs squared, where Cs is the speed of sound. This is speed at which pressure waves travel in a fluid. Okay. Now, from Bernoulli equation, this is from thermodynamics. From Bernoulli equation, delta P is approximately the magnitude of delta P is rho v del v. So, delta P is approximately rho d of v squared, this is rho v of del v, this is approximately. Okay. So, rho v del v, the magnitude of that is approximately is equal to C s squared del rho. Okay. So, del rho is approximately rho v del v by C s squared. So, we will substitute this out here. Okay. So, del rho by rho is rho v del v by C s squared rho is approximately is much small compared to del v by v. Okay. So, rho cancels to give you and del v, I mean let me use the same del v cancels. So, we will get that v squared by C s squared, the magnitude of that is very small compared to 1. So, when your velocities, the flow velocities are very small compared to the speed of sound, then density is approximately a constant. It is independent of the pressure changes that are there in a flow cannot cause sufficient density changes. So, when can that happen? When the velocity of the flow is very small compared to speed of sound. So, when v is small compared to speed of sound, you can treat the flow to be incompressible. Okay. So, this v divided by Cs, speed, the velocity of the flow divided by the speed of sound is given a special name, it is called the Mach number. So, when the Mach number is very small compared to 1, then the flow is incompressible. So, that is a very good approximation. So, now we know when you can treat the flow to be incompressible, but in practice we cannot say very small compared to 1 can mean is it very small, should Mach number be 10 to the minus 8 or 10 to the minus 3 or 10 to the minus 1. So, in practice, this implies in practice this means Mach number even if it is less than about 0.2 or 0.3, you can treat the flow to be effectively incompressible. It need not be very small in the sense of 10 to the minus 8 or 10 to the minus 5, it can be even just of the order of 0.2. Okay. So, since we know that for air the speed of sound at room temperature is 330 meter per second, then therefore, the flow can be incompressible, flow of air can be thought to be incompressible, air is incompressible for velocities less than 100 meters per second. For velocities of the order of 300 or 400 meters per second, of course, then the Mach number for air will become 1, therefore, we cannot treat air to be an incompressible fluid for such cases. Okay. So, but this is okay for many chemical engineering applications. So, we will not have such cases where velocity being of the order of few hundred meters per second in many chemical engineering applications. So, therefore, we can treat the fluid such as air to be practically incompressible, although air can be compressed, but the density of air does not practically change much for the pressure changes that are associated with in many chemical engineering applications. Okay. So, we will in this course we will largely deal only with incompressible fluids. Okay. Now, what is the importance of this continuity equation? So, we have this continuity equation for which for an incompressible fluid, this is general for an incompressible fluid, this means del dot V is 0. What is the importance of this equation? This is always valid. You cannot have a flow which violates this, because the continuity equation is merely a statement of conservation of mass that is valid at each and every point in the flow. So, we cannot imagine any fluid or any flow where the velocity profile violates this continuity equation as long as the flow is incompressible. So, that is a very important statement, that you have this constraint, that incompressibility constraint or the equation of continuity, that forces the velocity vector to be free of any divergence. That is, the divergence of velocity vector is 0 for all incompressible flows. Therefore, you cannot have velocity fields that have a positive or negative divergence in any given real flow of an incompressible fluid. Okay. So, we will stop here at this point and we will continue in the next lecture.